All right, 4.6 deals with directional derivatives. So I've got the theorem here, 4.12. So we're going to let z be this function that's got two variables, and you can do this with three as well, but we'll go over with two. Be a function with two variables, x and y. So these have to exist. The partial derivative with respect to x and the partial derivative with respect to y both have to exist. So the directional derivative of f in the direction of, we have u cosine theta plus sine I, u cosine of theta I plus sine theta j is given by, this is a notation for this. So this is the derivative of u, directional derivative of u with f of xy being our function. So this is going to equal the, here, let me change this. So this is the partial derivative of x of that function times cosine of theta plus the partial derivative of the y of that function times sine of theta. So, I mean, essentially this theta is going to be on the xy plane going in a counterclockwise method, similar to what you would see with the unit circle. All right, so let's see if we can try to figure out this problem number 263 first. All right, so our f of xy is going to be x times y, so we can find out the partials pretty easily. Derivative of f with respect to x is just y, because the derivative of x is 1, and y would be a constant in this form. Similarly, the derivative of the function with respect to y is equal to x. So we have those, and we'll need those. The other thing we're given that it's in the direction of this 1/2 I plus root 3 over 2j. Now, these numbers may be familiar with you, to you. These are typical for unit circle numbers to come up with given value, with a specific value of theta when dealing with cosine and sine. But instead of trying to work back and try to figure out what those are, we can similarly just find u, which we know to equal v over the magnitude of v. So our v is 1/2 I plus root 3 over 2j. And the magnitude of I will be what you would expect it to be. So first of all, we have this 1/2 squared plus 3 over 2 squared. Well, we've got a sine of a theta squared plus a cosine of a theta squared, so this should equal 1. We'll solve for it anyway. So 1/2 squared is 1/4. Root 3 squared is 3, and the other half is 4. So we do have 1 in the denominator, so it's really u is just the same as this 1/2 I plus root 3 over 2j. Now, ultimately, we're supposed to determine what it is at this point, 0 and -2. So we know we can rewrite this function here. Essentially, we have the derivative. Let me just change colors here. The derivative of u of this function is equal to y times 1/2, because that's what we have there, and plus x times root 3 over 2. So if we substitute in 0, -2, so we're going to evaluate at 0, -2, and that's going to give us, well, the y would be -2, so we have -2 times 1/2, and then we have 0 times root 3 over 2, and that just gives us -1. All right, so that we're done with that one. So here's a different flavor, sort of same sort of question, a little different with what they've given you. So they give us the f of xy, and this is number 74. They give the f of xy, so we can find those partials again. We'll need to do that no matter what. So derivative with respect to x is just 2x. The rest of it is all a constant, it goes to 0. And derivative with respect to y is going to be 4y. And the x stuff goes to 0. So what we have here, the derivative is going to be 2x, and then cosine of our theta, which is going to be pi by 6, and then plus 4y, sine of the same pi by 6. So that derivative is 2x, and cosine of pi by 6 is root 3 over 2, and the sine of that is 1/2. So ultimately we get the 2's cancel, so we have root 3x, and then 4 divided by 2 is 2, so 2y, and that is going to be our ultimate answer for this one. We're not evaluating this one at a point, they're just looking for the function.